In this session, we will learn about VI characteristics of a PN junction diode. V stands for voltage, while I stands for current. And VI characteristics imply a relationship of these two parameters and how they vary when diode is subjected to forward or reverse bias. The idea is to understand the diode behavior with changing voltage so that we can use the diode in a useful circuit. In previous sessions, we have learned that the electrons and holes move in opposite directions, and also their movement is different in forward and reverse bias conditions. Now, let us plot a simple graph to see this behavior. In forward bias, as we have seen before, the electrons and holes cannot move till they overcome a barrier potential. Let's draw the graph. This is V. This is I. V voltage is in volts. I current in milliampere. And this is the curve. Once the voltage is supplied by battery is slightly more than the barrier potential or voltage, then the current flows rapidly, rather exponentially. This transition point is called as the cut-in voltage. So this is for germanium, where the cut-in voltage or the knee voltage, cut-in voltage has to be greater than 0.2 volts, while for silicon it has to be greater than 0.6 volts. So thus, once the voltage supplied by battery is slightly more than this barrier potential, which is 0.2 volts for germanium or 0.6 volts for silicon, the current flows rapidly or rather exponentially. This is that exponential section. This transition point is called as the cut-in voltage or knee voltage. This is the transition point, which is the cut-in voltage or the knee voltage, and that should be more than the barrier potential. This is the barrier potential. Note that the graph is plotted in first quadrant. So if you think of this graph, this is the first quadrant, and this is the second quadrant, this is the third quadrant, and this is the fourth quadrant. So now the graph is plotted in the first quadrant, as in forward bias both voltage and current are positive. With increasing voltage above barrier potential, the current increases suddenly, as now more and more electrons and holes can cross over the barrier without any hindrance, and this keeps continuing. So does it mean with increasing voltage the current keeps increasing indefinitely or infinitely? Definitely no. The reason is, if you remember, when we manufactured our diode, we added a small quantity of dopant. This dopant or impurity was used to create P and N regions. Without these dopants, the intrinsic or original semiconductors were not pure metals. They were metalloids or semiconductors. Thus, they are not very good conductors. Now, with increased voltage, you have started the process of recombination. Recombination of free electrons plus holes due to movement across the barrier, and thus after a certain point this recombination stops based on the dopant level. The diode cannot offer more current and it has reached a saturated state. After that, even if more voltage is provided, the current does not increase, and thus you are just draining the battery. Also, increasing the voltage beyond a limit may damage the diode and make it not usable anymore. In reverse bias, we have seen that the electrons and holes now are moving away from the junction, and thus majority carriers are not there to cross the barrier. In this scenario, the minority carriers cross the barrier. Let's draw for reverse bias. This is I, this is V in volts, I in milliampere. So the graph looks something like this. Note that the graph here is plotted in the third quadrant. As in reverse bias, both voltage or battery voltage and conventional current, which is the minority currents, are both negative. So here this is negative and the current is also negative because it is reverse bias. The key thing to note is, unlike the forward bias condition, in reverse bias, the minority carriers are very less in number and hence the current is very low. So if you look at this current, this current is very small. So thus this is not milliamperes. In this case, this will be in nanoamperes, this portion. Also, unlike forward bias, in reverse bias, the minority carriers have to slide down a hill, if you remember the graph, and hence no barrier potential to cross. Thus, there is no concept of cut-in voltage. A small reverse voltage would give you a small reverse current. This is that small current. Reverse biasing is quite interesting. If you remember, when we manufactured the diode, we added dopants or impurities to create P and N junctions. This made uneven areas with excess carriers, and we called it majority carriers. We did not add or remove anything to create minority carriers, because the dopants only created more majority carriers. Now, the minority carriers were formed, or they always exist due to thermal conditions. It is the nature of physics. Thus, at a given temperature, they are constant, and thus, with increased voltage, these minority carriers do not provide an exponential growth of current like in forward bias. Hence, current in this stage is called as the saturation current. So, this portion is a small current, and it is called as saturation region. Because you cannot get more current with increasing voltage. If you see, this line is straight, so with increasing voltage in this direction, the current is constant. But an interesting thing happens when the voltage is continuously increased. After a certain voltage limit called the breakdown voltage, so this is that limit. This is called as breakdown limit. Now, if the voltage is increased after this breakdown voltage limit, then the current increases rapidly without any control, and the diode could get damaged. So why am I saying it could get damaged? Because there is a way to utilize this breakdown region in such a way that the diode does not get damaged. In fact, there are certain types of diodes which operate only in breakdown region. So, how does the current grow so fast? And how does the breakdown happen? There are two ways: avalanche breakdown and Zener breakdown. We will see about both these breakdowns in the next session.